In this section, we're going to be looking at using scientific measurements and most importantly, how to denote those measurements, how to report those measurements most accurately. So first of all, if we're looking at accuracy, when we report data, we want to be accurate. So accuracy is how close are we to the accepted value or the correct value that we're looking for. So if we're looking at it in terms of a bullseye, the correct or accepted value for a bullseye would be the most middle part that we could get. On this one, the center of the yellow. So how close can we get to hitting the center of that yellow would show how accurate we would be. Another term that we need to look at is precision. And a lot of times people think that accuracy and precision are the same thing. Precision is being able to repeat your data over and over. So, for example, if we look at this bullseye, these marks aren't necessarily accurate because they're not in the center, which is what we're looking for. But they are precise because they're all in the same area. So they're all in a repeated pattern. So we keep getting the same results. So when we do an experiment, or if we're trying to collect data, or if we're trying to hit a bullseye, we want to be accurate and precise, which means we would hit that center point over and over again. The next thing to look at is percent error. So percent error means how far off are you from what you're looking for. So the terms that we're going to use will be accepted value, and this is the value that we're trying to achieve, something that has already been proven. Maybe we're trying to find what temperature is water freezing in our freezer, maybe at different altitudes. So it has been proven that water should freeze at 32 degrees. So that would be our accepted value. In our experiment, maybe if our water freezes at 33, that would be our experimental value. So the experimental value is something that you actually have done an experiment and you get that new set of data. So to find how off we are, or what is our percent error, we're going to take accepted value minus experimental. Then we'll divide that number by the accepted value and multiply it by 100 to get a percentage. If we look at this sample problem, they're going to give us accepted value and an experimental value. So if we read through the problem, it says a student measures the mass and volume of a substance and calculates its density to be 1.4 grams per milliliter. If the student is actually measuring, like it says, then that's our experimental value. So we will write experimental value is the 1.4 grams per milliliter. The correct or accepted value of the density is 1.36 grams per milliliter. So accepted value 1.36 grams per milliliter. And so we are looking for the percent error. So percent error, we know, is accepted value minus experimental over accepted times 100. So we would plug this in. We've got 1.36 minus 1.4 all divided by 1.36 times 100. And that's going to give us a percentage of negative 2.94%. So when we get negative, that just means it's over the amount that we were looking for. And so if we were to look at 2 or about 3% off, really depending on what we're working with If we're off by 2%, it's probably not that big of a deal. If we're looking at smaller numbers, though, here we're looking at 1.36 versus 1.4. Depending on what kind of experiment we're doing, that may or may not make a big difference. But we would just have to look at what kind of data are we dealing with. If we're looking at a population of 50,000, 2% might not be a big deal. But if we're looking at measuring the size of a cell, it might be. When we look at what are called significant figures, we are looking at measurements that are going to include all digits of a number that are important to the measurement, plus a somewhat estimated calculation. So maybe if we are looking at the attendance at a ballpark, let's say that the attendance is reported as 12,500 people. Now at the gate, they probably can count exactly how many people entered that ballpark that night. It might have been 12,491. Does that mean that their 12,500 figure is inaccurate? It depends upon how accurate we need those figures to be. So we have to look at what is being reported, what is exact, and what is estimate when we're looking at significant figures. If we look at these different rulers, we can kind of see that if we were to give the measurement for the top ruler here, this is probably a liquid in a graduated cylinder. We could say that it's somewhere between the 2 and 3, probably 2, this would be 2.5, 2.6. So it's 2.6 for sure. But then we could estimate one more digit in that measurement. So maybe it's 2.65, 2.66. So that last digit would be an estimate in our reporting of that measurement. So we know that the first two are exact and the last one is an estimate. So those would be the significant figures in our reporting. If we look at this, maybe we have something that is exactly on the 2 for our measurement. So we could say that is 2 inches, or we could say it's 2.0 inches to be more accurate, to designate that, yes, it was right on that line. Because if I say it's 2 inches, it might be somewhere in this area that a person has estimated. But if I say it's 2.0, that would mean it was right on this line. So if I'm given a number, how do I determine how many significant figures are in that number? In your book, there is a list of rules, but I'm going to break it down to just a couple. So first of all, if you're given a number and there are non-zero digits in that number, all non-zero digits are counted as significant. They were for sure measured out. Then the zeros tend to give us some problems because sometimes zeros are significant, like in our 2.0, and sometimes they aren't. They're just placeholders, like if I said 12,500. I don't know if those last couple zeros in that digit are necessarily 100% accurate or if they were just rounded. So if we look at the United States, first of all, we need to identify that the Pacific Ocean is on this side versus the Atlantic Ocean on this side. So what I'm going to do is I'm going to associate the Pacific Ocean with a decimal present and the Atlantic Ocean with a decimal absent. If I am looking at how many significant figures are in each of these numbers, I'm going to be looking for the numbers that are exact in that measurement. So if I were to look at A, I've got 28.6. First of all, we said that anything that is not a zero is significant. And so since there's no zeros in this, we would have 3 significant figures. But at the same time, if we think about that Pacific and Atlantic picture, so we said the Pacific Ocean means that there's a decimal present. So if the decimal is present, we come to the Pacific side of that number. We come to then the first non-zero, which in this case is the 2, and we count everything that is left. So we've got 1, 2, 3 significant figures. If we look at B, again, the decimal is present. So we'll come to the Pacific side of the number, find the first non-zero, and then count everything else. So that would give us 4 significant figures. Looking at this next one, the decimal is absent. So I'm going to come to the Atlantic side, come to the first non-zero, which is the 1. So I'm going to count everything this way. So I'm skipping that 0 because that was probably rounded. So now this one would have 2 significant figures. On D, the decimal is present. Come to the Pacific side, go to the first non-zero, which is the 4, and then we're going to count everything left. So we've got 4 significant figures. On E, decimal is present. Come to the Pacific side. First non-zero is 6. So we're going to go all the way here. So this one would have 5 significant figures. The next thing we're going to look at is adding and subtracting with significant figures. So first of all, you have to be able to determine how many significant figures something has. And you can do these with your calculator. So the rule with adding and subtracting is you're going to look at the significant figures after the decimal. And the number with the least significant figures after the decimal. So this would have 1 after the decimal, and this would have 2. So our least amount after the decimal is 1. Our answer, once we've added it together, will keep the least amount, which is 1 significant figure. So if you can see, we're adding 2.1 plus 6.38, which on our calculator will give us 8.48. But since we only want to keep 1 significant figure after the decimal, we're going to round that 0.48 to 0.5. So that would be our answer. Now if we're looking at multiplying and dividing with significant figures, we're going to look at the total number of significant figures in the number. So if we start out with 4.67, that has a total of 3 significant figures. And we're going to multiply that by 3, which has a total of 1 significant figure. If I type that in my calculator, I'm going to get 14.01. But since the least amount of total significant figures in the number that I was multiplying only has 1, my answer can only have 1 total significant figure. So if I look at 14.1, I have to keep that value of the 14. So if I were to round it to 1 significant figure, I can get rid of the decimal for sure. So 14, if I'm going to round that to keep 1 significant figure, if I were to round it to 15 or 13 or keep it at 14, that still has 2. So the only way I can round it would be to turn that 4 into a 0. If it was 15, I would round it up to 20, but since it's 14, I'm going to keep it in the tens. So the answer for this is 10. Now another point to make, if I put a decimal after that 10, that would be 2 significant figures. So make sure when you have numbers that end in 0 like 10 or 100, you're using that decimal appropriately. Looking at a couple samples. So we are subtracting on the first one. Again, plug it into your calculator. So 5.44 minus 2.6130. We are subtracting, so we have to look at total after the decimal. So the 5.44 has 2 after the decimal, and the 2.6103 has 4 after the decimal. So we want to keep 2 after the decimal in our answer. So plugging it into the calculator, I get 2.8297. So I have to round that, so I have 2 after the decimal, which would give me 2.83. The next one, we're multiplying. So we're going to look at total number of significant figures. 2.4 has 2 significant figures, and 15.82 has 4. So my answer can keep 2 significant figures. So I plug it into the calculator and get 37.968, which then would round to 38 to keep 2 significant figures.